Welcome, this is lesson 19. In this tutorial, we're going to be talking about the register. So you can view this tutorial, the verilog code for this tutorial at projectfpga.com/tcp. Come down, select registers. Select registers. In the last tutorial, we talked about the register, which is a single block of RAM. Now today we are going to talk about the registers. So what are these registers? These registers are different storage of signals. These registers, we use them to store a huge lot of signal, which we saw throughout the tutorial. So our MAC address is stored in the register, and a huge lot of other signals which we use during the course of this tutorial. You can see some of them, IPGT. So all these signals are stored within the register. All of them come from the register, and more which we didn't literally bring out as a separate output here. So one thing very common about register is how do you read and write data. I will be demonstrating how the data is being read and written to. So we use the help of this multiplexer here. This is like the chief multiplexer of the whole circuit. When you go to the code, you are going to see this multiplexer. Though not all the inputs were used, so I tied them to 0. So this address is very important. This address shows the address of what register we are trying to read. Then this signal here is the chip enable. So let's first of all see where it comes from. You are able to read data only when this particular signal is 1. If not, you won't be able to read anything. And this is our data out here. So that signal is like our chip enabled. So let's see, I'd like to see where this chip enable is coming from. That is our register enable that enables output. So can we see is coming from here. So, and that is what we call our read bit. So let me explain what happened here. Here is a very crucial part of this circuit. This is where we do our read and write here. So this button here is the read write button. So whenever this button is high, we are doing what? We are writing. If it's low, we are reading. Yes, whenever it's high, we are writing. If it's low, we are reading. How do we do this? So this is like the chip select. Let me call it the register select here with the address also, but this CS, let me call it the register select. So it goes through this input with this read write. So whenever is high, this signal here, whenever is high, that means we are writing. So, and this AND gate is going to be on, and it goes up into the different register. We are going to come to that and see how it went up. Then this is for reading. So one of the criteria is telling it if the write select is off. That is, if this write select is off, therefore we are reading. And if we select any, so long as it's not 0, let it be 1. And this is what does our chip select here. Let me show you. This is it here, our chip select here. So one of the signals, one of the bits of the CS must be on for us to to read. So we have to know what part are we actually reading to or from. Then another thing is, now how does it do this? Whenever the register, so these are register bits which stores the location in memory of whatever data we are looking for. So let's see, I want us to watch this address, what it does. So in as much as this address selects which of the register data to output, this is what again it does. This multiplexer, this enable multiplexer, this is our chip enable select here. So I hope we understand up to this stage. So let's see what we did with this address here. So we compare this address with 0, 1, 2, 3. We check if this address 0, is this address 1, is this address 4, 5, 6, 7 and 8. We compare all of them. If is any of the address, if assuming here is 1, then right, okay, no, it's 6. Assuming the address is 6, then these 4 AND gates are going to common, and whenever they common, what next is going to happen is that I'm coming. Whenever these AND gates common, that is, if the associated comparator is true, the next AND gates are, first of all of the inputs are turned on. Then if we now select the read option, that is when this one is high, this bit is high, then it goes in here and is fed into this line here. So anybody on this line is going to receive the signal. So this chip select signal comes here and mixes with the so here is combined together here and here. Whenever they combine together, we get these signals here. So if the selected address is correct, this one turns on and brings out this input. Then this chip select chooses which of the AND gates is going to be turned on, and if they are chosen, as you can see, these are what the outputs of those AND gates are what feeds into our right signal of each register block. The right signal of each of our register block, this is the algorithm how is being gotten. That is the right signal of each register. Then the synchronization reset is tied down to 0. That is to say, you cannot synchronize. The sync reset is tied down to 0, so you cannot use it to reset the whole circuitry. Then again, the data in for all of them comes from one source, which is here. This is the general data in of the whole circuitry. It comes from one source, so it's up to the right signal to know whether it should allow the data to go in or not. So if the right signal is on, that is coming from these AND gates here, so whenever it's on, that means the input data is going to be stored into the RAM. So that's how this RAM is being how data is being stored in this RAM. And remember, they are all 8-bit RAM, but the data coming in is 32-bit data. So I'm obviously using wire splitter to choose the first 8 bits to go in. And assuming, take for instance, each of these AND comparators represents a group of register. Take for instance, this is a group of register. They are 4 in number, so they can share the same address but different chip select, different CS. So is this CS that comes in here, feeds in through here, and goes to each of these AND gates and choose which of them are we writing to. So all their outputs will still be connected together. Then the remaining output that was not used is going to be padded with 0. The remaining bits of the output that were not used is going to be padded with 0. Then again, all the outputs of each RAM is what is being fed into this multiplexer. All the outputs is fed into the multiplexer, and it's from there that we got all these other signals here, the content of the register. So when you go through the code, you see which particular register contains which particular data. So you can bring them all out and select. So if I can check, assuming this RIPGT, let me see. Oh, sorry. What is the problem? I'll go to the code. We are going to see which particular register contains which particular symbol. So this is a very complex, a very huge circuit, the register. We've been talking about it all this while. A huge lot of signals are set and used from this register, like the TSU's data is likewise stored in this register, and so on and so forth. So let me see. So that's that for this register module. Like I said, it's very important to understand that they are most times grouped. Example, this one is grouped. So whenever they are grouped, they are bound to share a group of common chip select enable, but they are still going to have the same address. So assuming they share the same address, so their group of AND gates is going to be on, but the chip select is going to choose which particular register is the data being written to. So I'm using this as an instance. So let's note that since the data going in is 32 bits and the register is 8 bits, the wire splitter is going to select only 8 out of each data in. Then there are times when data needs to be written to the whole group of registers, like this set of 4 registers. Then the data can be split 8 bits, 8 bits, 8 bits, and 8 bits, making it a total of 32 bits total. That is another way of storing data that is up to 32 bits total. If not, the wire splitter can remove other bits that are not being used, and here the bits that are not being used are actually padded with zeros. So then again, we can see the transmit pause timer value here, and the transmit pause request also, the hash algorithm that was used for CLC check. Then our MAC address also is here, then we saw the control data. We saw this, we have this we use this set of data when we are talking about the MII model. This is the clock divider we use when we are talking about the when we are studying the MII model also. So these are how all these signals are being stored in the register. So we can actually trace some of them back to see which actual register they are coming from. I see this IPG2. And trace it back to see. Okay, I'm trying to know what's happening here. Also, we can see the delay CLC enable, the CLC enable itself, the huge enable, the padding, the full duplex, the excessive differ enabled, the interframe gap, the promiscuous mode, the broadcast, the no preamble. So these are how all these data are coming from, how they are being stored and set from the registers. So you can, if you can trace which address each belong to, and you know the which chip select it is, you can either choose to read from it or write from it using what I already explained earlier. So this is how the register works. So when you go through the code with a bit of explanation which I've given, you'll be able to understand this register model fully well. So this is the code: projectfpga.com/tcp select the register array subcircuit, and you see everything I've just done. I think I'll be closing this shortly. Let me see. So this is it. Please subscribe to my channel for more tutorials like this. Okay, so this is it. This is where we set our temporary MDI data. When we are talking of the MII model, this is where the PRSD is being set in. So you need to study the register and know which of these signals, which part of the register do they belong to, what is the address, what is the chip select number, which value are you going to put there, and which value can you not put there. So all these are what you need when you are studying the register model. So this is how the register model works. Thank you, and subscribe to my channel. Have a nice day.